Hi, this is Mrs. Baisden, and this screencast is about significant figures. So first we need to talk about what are significant figures. Significant figures have to do with how a measurement was taken. So basically what they are is they are the numbers recorded in a measurement. And when you record a measurement in the lab, it's assumed that you do it according to this method. So any piece of equipment will have a limitation in terms of how precise it can be. So for example, if we look at this ruler down here, you can see that the ruler measures in centimeters, and it measures to the 10th of a centimeter. So if we look at this nail that we're measuring, we know for certain it's between 2.8 and 2.9. So what a significant figure tells us is it's all of the certain numbers plus an uncertain or an estimated number. So anytime you take a measurement, you have to be careful that you include that estimated number, because what you write down as your measurement is communicating something about the measurement device that you used to take that particular measurement. So if we look down here at the picture, this is between 2.8 and 2.9. So we know that for certain because those are the marks that are on that particular ruler. What we have to do then is estimate what our next digit is. So we know for certain it's somewhere between 2.8 and 2.9. So we know for certain the tenths place. Then our uncertain digit would be our hundredths place. So we would estimate, in this case, it would be 2.85. So this place right here is our estimated digit. So again, we know these for certain. We know 2.8 for certain, and then this hundredths place is our estimated digit because there are no marks. So we estimated how far in between the 2.8 and the 2.9 that particular measurement is. So when you count sig figs, when you have numbers that are on a piece of paper that were taken as measurements, but you can't see the measurement device, there's some rules that we use to count them. So for a non-zero integer, for a non-zero number, those always count when we're counting how many sig figs a number has. So for example, 25, those are both non-zero integers, so that number would have 2 sig figs. 1,352, again, all non-zero numbers, so those would have, that particular measurement would have 4 sig figs. If there are zeros, it depends on where the zeros are. So if you have things called leading zeros, which are the zeros in the front, leading zeros never count. So this number here, those zeros in the front are considered leading zeros, so this 0.0, those don't count, so we don't start counting until we hit the first non-zero number. So that particular number would have 1 sig fig. And then our next number down here, again, these are all leading zeros, so those don't count. We don't start counting until we hit the first non-zero number. We count everything afterwards, so that number would have 3 sig figs. Another type of zero we can have is a captive zero. And what a captive zero is a zero that's trapped in between two non-zero numbers. So this zero here would be a captive zero, as would these zeros down here. So those would be captive zeros. So those count because they're in between non-zero numbers. So this first number up here, 101, that would have 3 sig figs. And then our second number, we wouldn't count this first zero, so this first zero is a leading zero. We wouldn't start counting until we hit the first non-zero number, but then these zeros count because they are captive. They're trapped in between non-zero numbers. So this one would have 1, 2, 3, 4, 5, 6, 7 sig figs. Another type of zero you can have is a trailing zero, and these only count if there is a decimal point. So for this one, this first number on here, there's no decimal point, so these are our trailing zeros. They don't count. So this one is only 1 sig fig, so that first digit is the only one that actually counts. Now if we put a 0 there, that makes those zeros significant. And again, that's communicating something about the device that that measurement was taken with. So this tells us it was measured all the way out to this place, so this one would have 4 significant figures. This next one, this 0 is significant because of the decimal, so that number would have 3 sig figs. If you have an exact number, like a number you count, like if there are 12 pieces of aluminum or if you count a number of anything, those don't count, or those have an unlimited number of sig figs. So when we go to actually calculate or do something with those numbers, they don't limit the number of sig figs in the answer. So they have an unlimited number, so we don't worry about those. Conversion factors are the same way. So if we say that 1 meter equals 100 centimeters, that would also not count when we're looking at sig figs. Those have unlimited numbers of sig figs. And then the last ones we would look at are numbers in scientific notation. Anytime a number is in scientific notation, all of the numbers before the 10 to the n count. So in this case, this number would have 2 sig figs. And in this one, we look at all the numbers before the 10 to the x. This would have 1, 2, 3, 4, 5 sig figs. Okay, so let's look at a couple example problems and go through and see if we can figure out how many sig figs in each. So our first one, these are all non-zero numbers, so this one would have 3 sig figs. For our second one, we've got a captive 0, which counts, so that number would also have 3 sig figs. Our next one, we've got some leading zeros, so in that case, those don't count. We don't start counting until we hit the first non-zero, so that would have 2 sig figs. And then once we hit that non-zero, everything after it counts. This one down here, we've got captive zeros, so those count, and we start all the way at the beginning, so this one would have 1, 2, 3, 4, 5 sig figs. Okay, so here's another set of practice problems. So what I would suggest you do is stop the video for just a minute, do some practice with those, and then once you've gone through and tried them by yourself, hit play again, and then we'll go through and see how you did. Okay, so my first one, as soon as we hit the first non-zero digit, we start counting, so this would have 3. This one, trailing zeros without a decimal, that would only have 1. Captive zeros, that would have 4. This one has a trailing 0 with no decimal, so that one doesn't count, so this one would only have 1, 2, 3. And then our numbers in scientific notation, that first one would have 2. Our next one would have 4. Now when you have to round to a certain number of sig figs, we're basically going to follow our same rules that we use in math. So for example, if the digit removed is less than 5, then the number stays the same. If it's greater than or equal to 5, the number is increased by 1. And then if you have a series of calculations, you always leave extra digits till the very end, and then you round once you've finished all your series of calculations. So again, you probably don't need to write these down. These are the same rules you use in your math class. Okay, so let's look at a couple examples. So this one, the first one, it says round all of these to 2 sig figs. So this is where I'm going to round. So I look at the number after. That number is greater than 5, so I'm going to round this to 2.2. This one down here, I want to round it to this digit here, to 2 sig figs. So this one is going to be 0.00035 because the number that I'm dropping is less than 5, so I leave this number the same. My next one, I'm going to round it to 2 sig figs, so this is where I need to round. So since this number is greater than 5, I round up, so this becomes 130. And then my last one down here, 2 sig figs, I need to round at that place. This number is greater than 5, so I'm going to round this to 11. Okay, same deal here on the practice problems. Go ahead and pause the video for a second. Go through. Round this time to 3 sig figs. And then come back and check your answer. So this first one, I'm going to round to 1.27. Next one, 0.0506. Next one, 1,560. And my final one, 125,000. And again, notice that these numbers are very similar to this number, it's just rounded. So this one, notice this last one, I didn't round it to 125 because that would be a very different number than 125,421. So the numbers should be communicating about the same magnitude, but again, it's just a rounded number.